When you look on the periodic table, as I taught in an earlier video linked to in the description below or floating over my head somewhere, you see all these atomic weights or masses listed for the different elements. For example, I think on hydrogen on the periodic table it lists it as having a mass of 1.022 or something like that. In reality, however, there's not any hydrogen atom that weighs exactly 1.022 or whatever it says on the periodic table. So where does that number come from? Well, that number is actually a weighted average that takes into account the different isotopes of hydrogen. There's hydrogen 1 that weighs exactly 1, hydrogen 2 called deuterium that weighs exactly 2, and hydrogen 3, much rarer, called tritium, which weighs exactly 3. And they exist in different percentage abundances out in nature. So we multiply and add them in a way that gives us a weighted percentage that takes into account sort of the weighted average of all of those, and that's where that number 1.022, or whatever it is on the periodic table, ends up coming from. Does that make sense okay? So this problem gives us different masses of what we colloquially call copper-63 as having this atomic mass, and copper-65 as having this atomic mass, with these respective percentages. So in order to get to the weighted average atomic mass that we get on the periodic table for copper, what we do is we take each of these numbers, multiply it by its respective percentage, and add them together, okay? So we're assuming, of course, based on the info provided in this problem, that these are the only two isotopes that exist for copper. And I think that turns out to be the case. Don't hold me to that, okay? So what I'm going to do is take the 62.9296 and put it here. And when I multiply it by its percentage, I don't multiply it by 69.17. I have to multiply it by its decimal percentage. That is, I take 69.17 divided by 100 to go back to what the decimal percentage is. So that's 0.6917. Does that make sense? So I've got those clustered together, and then I separately add to that these analogous terms, 64.9278 multiplied by the decimal percentage version of 30.83. That's 30.83 divided by 100, okay? You punch all that into your calculator, and you end up getting this answer right here, at least I hope, 63.5456, which is what you'll see on the periodic table for the atomic mass of copper. Now when you see that, please keep in mind that in reality there's no such thing as a copper atom that actually literally weighs that. Instead, what we're seeing is a weighted average that takes into account the relative percentages and different actual weights of the two different isotopes of copper.